Hi everyone, are you able to hear me now? Can you see my screen clearly? All right, wonderful, wonderful. So, okay, so there are a couple of questions. One was related to NLP, time series, and so yes, let me just, with respect to time series, I'll have to take a look. And so far we had not planned for time series as such. And there are a couple of more XGBoost, for example, though let me see if we can add and which part is needed. Okay, so the other question was from Bintao related to the assessments of chapter 6 to 9. So yeah, those will be appearing very soon. We just have to make the assessments visible. And with respect to topic 5, the review of the project. So we will discuss it probably after this. Okay, great, great. Hi Balaji, hi Bintao, hi Ji, hi Gopi, Kamal, Noor. Great to have all of you in the session. All right, so let's start. Great, great. So yesterday we talked about, we learned about the ensemble, and we mostly learned about how to do the processing in parallel. Okay, so we also explored the something called feature importances, and that that will go more detailed into the reducing the number of dimensions in the next session. All right, so great, great. So so then we started yesterday about something called boosting. Instead of doing ensembling in parallel, if we ensemble in sequence, the okay, so instead of doing it parallel, we do it in sequence. A question is, from Kamal, that how is feature importance number calculated? Feature importance number is based on the height, on which the width or the average height of a feature to appear. Okay, so like the way it is. So since petal length appeared as one of the criteria, okay, because we are splitting the node at the top. So we basically find out about each feature on the basis of which we are splitting the node, and then uh, and then and then compute its average height in the tree. Okay, this one is a depth 0, this one is a depth 1, and so on. Okay, that's how we compute the feature importances. All right. Okay, so petal length feature importance is 0 in this case, as in the, how should I say, uh, let me show you with respect to the numbers. All right, so All right, so in this case, I'll have to see if we could go it really up. I think this would be part of decision tree as well, right? All right. Okay, so okay, so you can see that the feature importance of the first one is 0, and then second one is 1. All right. All right. So here I think we only took the two features, right? On the basis of which we did the Y. Yeah. So yeah, 0, 1, 2. Okay. So coming back to it, basically the feature importance is computed as petal length and petal width. So here in this case, the importance of this one is going to be 1. All right. Okay, let me go back. Hmm. All right. So the way feature importance is actually calculated is we take feature the depth, the average depth. So this one is at say 0, and the average depth of this one is basically 0, and here the feature importance is basically the average depth is 1. Therefore, so I think it has to be inverse of it. That's what I was trying to allocate. So, so the exact formula I need to take a look. That's what I was trying to figure out. So the way it's computed is the average depth in the tree is computed, and then so it is possible to get the estimate of features importance by computing the average depth at which it appears across all the trees in the forest. Okay, and so okay, never mind. So I think the we could. I'm just trying to figure out the exact formula. I think there would be a way to do it here. Okay. So here the feature importances is this and this. I think this would give you a better answer. All right. So here we have feature names that we created earlier that from where we have picked it up. Then we have feature importances, and then we are jipping it. And okay, they are in the same order in which we have used the target variable y. Okay, so yeah. So I need to figure out exactly what formula it uses, but it is very clear that it is based on the average height in the tree. Okay, based on the average height in the tree. Never mind. So I think we can probe it further at a later point of time. Good. So further point is that I wish the feature importance is also stated, which is the feature. Maybe the most deep one is considered at 0 and the one nearer the root is considered 1. Looks like that. Okay, looks like that. So because the feature importance is something between 0 and 1, and the more important the feature is, bigger is the number. The most important feature which is there is going to get 1, while least important going to get 0. Okay, so that's what about feature importance is. And all right, good, good. So the next thing we are going to discuss is about how exactly AdaBoost work. Okay, so so boosting is about chaining the various predictors. The output of one goes as input to another, and before giving the input, there are some changes that are done. Okay, so there are two basic methods of boosting. Boosting is the idea whereby the predictions of one are improved by the second one, and boosting is mostly chaining. Okay, so one way for a new predictor to predict is to correct its predecessor predecessor is to pay a bit more attention to the training instances that the predecessor underfitted. Okay, so basically it would pay more attention to the AdaBoost. In AdaBoost, the second predictor would would try to pay more attention to the instances which are misclassified or did wrong predictions in the first case. So basically, if there's a predictor one, this diagram actually makes it very clear. So here, let's say this is your data and this is your first base classifier. This is a first classifier, or we call it base classifier. Now, this one is giving certain results. At this point of time, we do the instance weight updates, meaning we figure out what is wrong, which are the instances which are wrongly classified with this. So at this point of time, we do the fit, just after fit, we also do the test, and then we observe which of the instances are wrongly classified, and then we fix those parts. We basically increase the weightages of those instances. Remember, we are increasing the weightages of those instances. And then again, after increasing those weightages, we again feed it to the second classifier, and then the chain continues. Okay, so here just after finishing the classification, weight updation would happen. Okay, so the decision boundaries of 5 consecutive predictors of the moon's dataset in this example, each predictor is highly regularized SVM classifier with an RBF kernel. So each predictor here is an SVM classifier with RBF kernel, the one that we went through earlier. So here you see that there are 5 predictors, 1, 2, 3, 4, 5. The fifth one is doing a really good job. The first one was underfitting. The second was a little more underfitting. Okay. The third one was a little more underfitting, and fourth one was, sorry, second one was less underfitting, third one was further less, fourth one is, and so on. So fifth one is doing a very good job by basically doing less underfitting. Okay, I'm going to talk about the weights just after this. So the first classifier gets many instances wrong, so their weights gets boosted. The second classifier therefore does a better job on these instances, and so on. Okay. So the same sequence of predictors, except that learning rate is halved. We'll talk about learning rate. So every time one instance gets wrong, the second one, one predictor gets wrong, the second one starts performing on it. First one got these blue ones wrong, and as well as the green one's wrong. So second one basically improved upon it. Now how much should it improve? How much should it improve is a function of so, applying the weights. How heavily are we applying the rates? That is basically called learning rates. Okay, what coefficient should be the multiplied to the weights? Okay, that is called the learning rate. Here the learning rate is slow. Here the learning rate is standard 0, and therefore this one is far more slow, and this one is faster. Okay, faster in converging, just like gradient descent. Okay, so basically, in case of gradient descent, here the second algorithm is second predictor is improving upon the first predictor's um, predictions, while in case of gradient descent, the second step improves upon the first step. Okay, so that's the difference. That's how there's a similarity and the difference between AdaBoost and gradient descent. Okay, we'll talk about learning rate mathematically, then it'll make more sense to put that in place. Okay, all right. So with respect to predictions, once all the predictors are trained, the ensemble can make the predictions very much like bagging or pasting, except that predictors have different weights depending on their overall accuracy on the weighted training set. Okay. All right. Now, so again, AdaBoost is a sequential learning technique. It's a boosting algorithm at the end of the day, and it cannot be parallelized. Okay, or maybe partially the algorithm could be parallelized, but in general, the second algorithm only starts working. The second predictor only starts working when the first predictor finishes. Okay, therefore, a sequential learning technique. You cannot do it parallel. All right. So it doesn't scale well as compared to bagging or pasting, but it might produce a better accuracy. All right. So let's try to understand what goes in the backend. So there is something called weights. With those weights, we are going to multiply. We're going to compute the numbers with which we are going to multiply the instances. What is an instance? In case of, let's say, image, the MNIST data, every image was an instance. Okay, every image, all 784 pixels were part of one instance, right? So, okay. So in the beginning, what we say is that M is the total number of images, right? In case of MNIST, the test data had 60,000 record. So M was 60,000, correct? So, and each instance weight, WI, is something that we are defining here. We are saying that we come up with a number called W for each instance. Okay, so first of all, in the beginning, the value of M will be 1 by 60,000, right? 1 by M. Value of W would be the 1 by M. Okay, so we come up with these numbers, WI. I stands for each of the instance. Okay, so in the algorithm, we basically come up with the WI. Initially, we set the value to this. Now, for the first predictor, while training the first predictor, the is trained. So whenever for every predictor, what we do is we compute the average weight. Okay. So first, we sum up the instance weights of all of the instances which failed. Okay. So we sum up the weights of all the instances which have failed, okay, and divided by total weights, okay. So initially, in the first case, if you think about it, some of the instances will fail, and therefore this value will be computed. So summation of all the weights of the instances that have failed and summation of all the weights. So summation of all the weights for the first time, how much will that be? It will be 1. 1 by m added 1 m times, correct? So initially, this is going to be 1. That's right. And then here, it'll be lesser than 1. So let's say out of uh, out of 60,000 instances, we got 50,000 instances correct, okay? And 10,000 failed. Okay, that means it is going to be 1 by 60,000. So it is going to be 1 by 6, correct? Let's say only 10,000 have failed, as in when we did the prediction on those 60,000 instances, the basically the it has failed on it has not performed well on 10,000 instance. Therefore, we're going to take care of only, so it will be 10,000 times 1 by 60,000, right? That is the initial one. So the R at the first predictor, Rj here means J for jth predictor. Now J is 1, so Rj is R1 is equals to 1 by 6, right? 1 by 6. So initially this would be the case if, let's say, there were 10,000 cases were missed by the first predictor. All right, is it clear, the formula? We have not yet recomputed the weights. We are just computing R yet. Now, here we are saying that sum up all the weights where the predicted value is not equal to the actual value. Okay, predicted value is not equal to the actual value. Wherever is that, we sum up only those failed instances. So this coefficient says that how underfitted did how much underfitting did our algorithm. Okay, if our algorithm did really bad underfitting, then there will be more instances which have failed in prediction, and therefore it is going to be more. Okay, correct. If RJ is basically performing good, then the as in jth algorithm is doing good, that means RJ would be really low. Okay, so here we are saying not include jth. Here we are saying the predictions of jth algorithm, yj, and for ith instance, Okay, so while we apply, let's say we run our algorithm on MNIST, okay, and we are in this J means there could be, let me just go back to this diagram. So here, this is J equals to 1, J equals to 2, J equals to 3, J equals to 4. Okay, all right. So for R1, R1 basically this value, this will be predictions of R1 and sum up only the weights where the prediction was not equal to the actual. Yes. Okay. Question from Gopi. Zero is good as it's counting the misclassified instance in the numerator. Um, yes, zero is good. Okay, zero is good. Okay, let's say there was for all the things it was equal, right? Predictions were actual, equal to actual, and therefore there will be no such weights where the predictions are not equal to the actual. Therefore, the weights will go zero and Rj will be zero. Okay. Yes, Noor, and I'm really sorry to confuse you. So yes, so zero will be the correct one. One will be the case where it gave error in all of the cases. All right. Is it clear to everyone? So question point from Binta is that Rj is a weight which does not include jth wj, right? Rj is the weight, okay, which does not include Rj is the weight which does not include jth wj. Okay. Okay. So okay, let me again say. So actually, I think what I should do is I should just go back here and this something that we can explain. Why I am explaining this is and so that we become comfortable with these symbols. Okay, these symbols sometimes look really confusing. Let's say we had say 4 instances. Okay, let's say we have 4 images: image 1, image 2, image 3, image 4. Okay, and we applied an algorithm on this. We basically apply, and here in all of these we have say y. Okay, all right. Okay, so these are basically the features. This is the features. Okay, and there are 784 features, right? 784 features. Columns basically it has 784 pixels, and this is our target variable. Okay, this is our target variable that this is 5, this is 1, this is 2, this is 3. Okay, so these are instances as M, and these are called N. Okay, these are called N. So here M M is this now, right? So we basically fit this. Okay, we did fit on this. Okay, and we initially initially what we did was we assigned weights to it. How much weight would be? 1 by 4, right? There are 4 amps, so initial weight will be 1 by 4, 1 by 4 to all of these, correct? So the weight, the W, uh, WI, as in I where I is going from 0 to M, right? 0 up to and less than M. So basically WI is this. So when we say fit, it's going to do something, and then we do test. Okay, fit followed by the test. All right, my handwriting is really okay. So we did fit followed by a test, and then when we did, when we, as in test as in predict, okay? So when we did that, we found out that our algorithm is predicting as, instead of 5, it's predicting, say, 3, and here it's predicting, well, it's predicting 2, and it's predicting 3. So the R1 is going to be how much? R1 at this point of time, R1 is going to be, R1 is going to be, so when we sum up, only this one will sum up, correct? Because that's the place where this is our y predicted, okay? And this is our y actual. Okay, this column is our y actual, this is y predicted. So we are going to go from everyone to everyone, and we're going to say, is this not equal to this one? Only then count the bits. So it's going to be 1 by 4 in the top, right? Divided by summation of all of the 1 by 4s, which is 1, correct? So the R is 1 by 4. All right, did it make sense to you? Abhinav, Balaji, Gigi, Gopi, Kamal, Shahrukh, Noor, Pratik, and Ross. Okay. This is kind of a refresher on the symbols that we studied earlier. Okay. All right. That's good. If you're clear till here and not clear what happens next, okay. So don't worry. All right. So yeah, I'll just keep it somewhere. Yeah. All right. So basically, this is what is happening there. So we're computing the Ri. Okay. The Rj, not Ri. This is Rj. Okay. Now at this point, so everybody is clear about this, right? Next is we compute something called predictor's weight Aj. Okay. And it is basically the logarithm of this coefficient. Okay. So if Rj is 0, that means it's going to be infinite, right? If the Rj is doing really good with respect to prediction, and so the Rj is small. Rj is small means it did a very small misses, right? It missed less. So if Rj is really small, this number is going to be um, this number is going to be smaller, right? This number is going to be bigger actually. 1 by Rj minus 1, right? So as Rj increases, Rj decreases. As Rj decreases, this number is going to increase. Okay. As Rj decreases, this number is going to increase. And hence, the alpha will also increase. Okay. So as the, what do we call this? This is called error rate. So the, okay. So the error rate here, Rj, is going to be, if this is going to be really really small number, this is going to be the big number. Okay. All right. So Rj is the error rate, and if Rj decreases, this number is going to increase. Okay. And if Rj, if there is more error rate, if more error rate, then this number is going to be small. Is it clear? So the predictor's weight alpha is something we are coming up. Alpha is basically also a result of a coefficient here. It's called learning rate. Okay. So the more is eta. This is called eta, the learning rate. More is eta, the more is going to be the the more is eta, the more is going to be the predictor's weight. Okay, so this eta is generally a function of our learning rate. It's a function of our learning rate and the error rate. Okay, so now once we have computed this, okay, so the more accurate the predictor is, the lesser is going to be RJ and higher its weight will be. Okay. The more accurate the predictor is, if the jth predictor was really good, then RJ will be really small and hence this predictor's weight will be higher. Okay. If it's just randomly guessing, the weights will be close to zero. Okay. Weights will be close to zero. So if let's say there is a so because RJ will be close to 1 and hence the the alpha, the predictor will be close to 0. Okay. So RJ, if RJ is 0, that means no error, right? And hence it's going to be basically 0. Okay. So the weight is going to be kind of infinite in case the error rate is 0. All right. So a question from Gopi. So this formula is applied to all the weights on each boosting iteration, then RJ is reevaluated. That's correct. Okay. Okay. If RJ is really high, it's let's say 0.99 or something, which means error rate is high, which means the algorithm is often wrong. Okay. So RJ is going to be really big, like 0.99 or so. If it is 0.99 or so, what will happen is the weights will be negative. Okay. Weights will be negative. Okay. All right. So this is about computing the weights. Now the next step is important. Now what it does is whatever is the predictor's weight that we have computed, it does some e to the power of that one. If the predictions were correct, it'll leave the weights as such. If the predictions were wrong, it will multiply all of the predictions with this number. Okay, with this number. So it's a constant, it's a new weight. New weight basically all of the instances are multiplied by same number. This is a very important part. So all of the instances which were misclassified are being multiplied by this number. Okay. Clear? No. So if eta rate is if eta is negative, even then the this exponent is going to be tiny, not negative. Okay, this value is going to be tiny but not negative. Okay, that's right, Noor. Okay, a question from Gopi is why would you set learning rate negative? Okay, if the error rate of our program is really high and we would like to keep the instances from being multiplied by huge number, then we would generally keep the learning rate as low. Okay. Okay. So again, the eta is the hyperparameter which you could experiment with. All right. Is this clear? So basically, all we are doing is we are computing error rate, how much was the error, and multiplying with that some variant of the error rate. Okay, we are multiplying some variant of the error rate to all the instances. Okay, okay. So the second algorithm would see a bit of emphasized version of these weights, and we basically reducing the we are leaving the weight for each one as such. Wherever we have classified it correctly, we are leaving the weights as such. And wherever it got misclassified, there we are multiplying with a constant number. This constant number is a function of how much mistake did we do and at what pace do we, this constant number, this number is a function of how much error did the algorithm do and what is our learning rate. A question from Noor is, but is not analogous to slow memorization? Not really, not really. We are just emphasizing the weights, okay? Emphasizing the weights. So, so our algorithm has ignored, it's like opposite of regularization. In regularization, what we did was we tried to decrease the impact of the weights, right? Whereby the here why we are doing it is because our program is underfitting and we want it to kind of force it to look at those instances. So it might look like it is kind of memorization. We are trying to force it to look at the instances which it left. Okay. So it is kind of, yes, in that way, when I'm coming to think of it, it's kind of slow memorization, right? So it's like, okay, it's like you're preparing for GRE and you have to memorize the words, right? You're preparing for GRE, you have to memorize the words. And the software, it observes how well you are doing on certain words. So it keep on removing those words while it'll keep on increasing the the words that you are kind of forgetting all the time. Okay, so that's a kind of, I mean, that's actually the one I built earlier in long back. So it used to display the words and you have to type it used to display the answer and you have to type the word. And in case you did it perfectly, then it'll kind of ignore that in the next round. Okay, so that way basically, so the software was doing the boosting on you, as in it'll show in the next round, it'll kind of keep on removing all the words which you have memorized. So yes, okay. I'm not sure if that software is around, but last time I saw somebody using the same software. It was a desktop application, and I don't remember where it is now. Okay, so again, so basically that's what it was doing. That's what we are doing here. We show it images and observe that on which image the algorithm did well. Now, instead of completely removing the images, we basically decrease the weightage decrease the weights, and multiply all the say pixels, all the pixels with the weight. Okay. Okay. So yes. So dynamic difficulty adjustment is one term. Okay, that yeah, that is also we can use to explain the behavior. So is this the same thing happening here? The next predictor will not be having all the samples that got it right. It will be having all the samples, just that their weights will be as such. Their weights will be 1 by m, and the weights for the one which got misclassified will be more than 1 by m. Okay, and the weights will keep on increasing if the okay. All right, so now these weights will again be normalized, which means that they'll basically become, this will become one, and this will become, these will kind of become one or more, and this will become lesser. And then new predictor is trained using the updated weights. Okay, updated weights as in, let me go back. Okay, yeah. So these weights are what we multiply each instance vector with. Remember, we had in instances there were pixels, we had standardized those as well, and then we multiply these weights uh, to all the instances, and then we train. Okay, okay. Let me try to understand the question. Question is, I do not understand decrease the weightage of a sample, because when you are running the algo, you either have a sample or you don't have a sample, right? Right. Let me go back to the diagram. So here, let's say these are the pixels, right? These are the pixels. Now, okay. So, yep. All right. So question is, what does it mean by a new predictor is trained using updated weights? Any suggestions? Probably that's your question, right, Kamal? What does it mean by how is new predictor trained using updated weights? Any suggestions? Anybody? What does it mean by the sixth sentence? Okay. All right. Good. Okay. Now, when we say basically, what does it mean by computing the weightages? So here, when we said WI, right? So all we did was we multiplied these instances, okay, their pixel values with this WI. Okay, there'll be pixel values of each one. So we multiplied with all of these by 0.25. Okay, all of these got multiplied with 0.25, right? So we basically multiplied all these pixels with 0.25, leaving y as such, and then did the training. Okay, so that's what it means by doing the fit or doing the predict based on the weightages. All right. And similarly, these W's will again be computed at this instance. Again, W's will be computed here. And W, we understood the process, right? By computing the alpha. Before that, first we compute the error rate, then we compute the weightages, and then we compute the weights. And then we multiply these instances, these instances after multiplying with W, with this new W, and then again do the training. Okay, so basically all these pixel weights will be multiplied by 0.25 earlier, and then when we decompute Wi, we are going to multiply with a new number now and do that. Okay. Okay, am I correct? Okay. Hmm. So yeah, so here question is, are we adding a new column with the weights, or are we ignoring, are we multiplying the features with the weights? Okay, so Noor's point was that maybe we are just keeping the weights as one of the columns, and then we are repeating the process and doing that. So in that case, I'm not sure if that would improve the emphasis of the features of the particular instance. Okay. Okay, I'll come back to that, Gopi and Ross. Okay. So, all right. Am I making sense to you? All right. So so as per my understanding, what happens is that so one of the ways of basically including weights into the training is add W as one of the columns here, right? That's what Noor is suggesting, and then train our algorithm on it. Correct? Is that what you are saying, Noor? That will just basically add, say, um, these weightages as one of the weights here and do the computation, and so no, actually, in that case, what will happen is this weight is not bringing the emphasis to the features of the one which are misclassified. The what the objective is to look at the so since these pixels are is normalized, right? All these pixels will be normalized. And after normalization, what we are doing is we're multiplying with a coefficient, right? All of them. that would basically improve the learning, because we are saying that, hey, you forgot to look at this particular pixel, this kind of pixels, you are ignoring this particular kind of pixels, by multiplying, by increasing the emphasis of those instances which were misclassified. So my understanding is that, but I can reevaluate. I can take a relook at it. So basically the 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 weightage of instance would be something that get applied on the instances. Okay, y will remain as such, y will remain as such, while x will get multiplied. Okay, does it sound reasonable, all of you? Okay, go ahead. So what does it mean by this? Then finally, a new predictor is trained using updated weights. Okay. Okay. So we are saying that for these features, try to predict this. Okay. What does it mean by training some algorithm? We are saying, hey, these are the features, these are the pixels, and for these pixels, the outcome should look like this. For these pixels, outcome should look like this, and so on, right? So the outcome remains as such. It's just that we are saying that, hey, you forgot this corner once. This is how it is looking. So please look at these. Look at this kind of pixels also. Okay, and but the outcome is still the same. All right. Okay. Just think about. Let's say you're training somebody, and okay, and you basically saying that this is how the image is, and you realize that this person is maybe colorblind, so you increase the emphasis of a particular color by multiplying with the coefficient which were misclassified, and then let it do that. Okay. So training remains the same way, while the prediction remains that. Okay. All right. So if we decrease the emphasis, what will it do is it'll start doing overfitting very quickly. Okay, and the learning would become, because see, the number of unclassified set will be really low, right? Let's say 10% is misclassified, because if somebody is classifying even randomly, 50% of the record will be correct, right? So every time, even if you are using a random classifier, it will end up classifying 50%, and therefore you will end up with only 50% of records. Okay, and in the end, you will be convinced that, okay, and as the number of records keep on going down, your learning will keep on going down, right? Very good set of questions, and these are the questions that would help us understand its behavior. Okay, right, Kamal? So basically, instead of ignoring, why if we just ignore, right, even the worst um, classifier, even the worst classifier, the one which is just doing a coin toss, it'll end up with 50% of the records, right? And 505 case, we'll be left with only say 10% of records in a single shot. Correct? Remember our 505 case, right? In which the accuracy of a random accuracy of not 5, really dumb classifier was actually 90%. Okay, all right. All right. A question from Kamal is that I'm not sure that we just scale X, not Y, right? So, so we are saying that this image is 5. Okay, let me try, because this is something that I also had the same questions when I was trying to figure out the behavior of this one. So question is, um, why are we not, so is everybody okay that we are scaling the instances which are, we are scaling the or zooming in, we are zooming in on the instances which are the outcome, right? Zooming in on the instances which are misclassified. Now question is, why are we not multiplying y, right? See, the y is the objective function here. Okay, this is our actual raw data, right? So we fiddle around with the raw data, but the actual classifier is something that we need to predict. Okay, imagine that multiplying 0.24 with all these numbers. So this will become how much? It'll become 1.25, it'll become 0.25, and so on. So this is basically our prediction. This is something which we have to predict. And so we are still saying that, hey, this, let's say there is this image, right? And our algorithm is saying that this is 3. Okay, and this image looks like this. Okay, so so here we realize that, okay, maybe the pixels are not that shiny enough, so we just increase the pixel weights a bit. Okay, then maybe it'll be able to classify it as 3. Okay, so basically we are kind of aiding the classification. Okay, I'm not still very convinced with my answer. Okay, all right, all right. Okay, so basically the idea was to, in case, let's say the um, we realize the weakness of the algorithm, that it is not doing well on this kind of instances. So we try to emphasize on those instances and hope that the algorithm will get it. Okay, so a point from nowhere is, maybe we can code this example and see if it really helps in understanding the visualization. Yes, we can try that, but it'll be difficult to do it in the this time. Okay. Okay. A question from Ross says, this is similar to training a neural network. Yes. So it's a very good, important point. So most of the ensemble actually partly was like neural net. Okay. And just that neural net has a different way of coming up with the values. Okay. Okay. So it's kind of, yes, neural network. Now, next question from Gigi is, will it fit for all algos? For, yeah, will it fit for all algo? So basically, for all instances, do you mean? Will it fit for all instances? Is that your question? Okay, okay. So let me go back to the diagram. Okay, here. So this is what is going to happen. So the first algorithm will we will be learning from this raw data by multiplying 1 by m here, the initial weights. Then then we are going to do the first classification, and then we will update the instance weights. Okay, we'll update the instance weights, and afterwards we are going to multiply. We're going to we afterwards we are going to use this data for the second algorithm. So these are the algorithms which are being used for first fit and then predict. Okay. So between the two algorithms, it is going to do the weight updates. Did I understand your question correctly, Gigi? Okay. So between each two algorithms in sequence, the weights will be updated. A question from Kamal, but what about regression? Is not AdaBoost used there? Then why say price of the house remains same when we scale the area of the house? Okay, all right. Interesting question. Interesting question. So yes, question is here when we are updating the instance weights, why are we not updating the y? Okay, okay. So in case of regression, let's say we multiply the instance and this. So what will happen is if you take a look, we multiplied this value with this with certain weight. We also multiplied the y value, right? So as a consequence, what would happen is the effect of each instance still remains the same, right? For a price of say for X feature, the value of it has also increased. Therefore, the the impact of those factors is not going to come into the significance. Okay, if we also multiply the right side value, because the end result remain the same, kind of same, not really same, but yeah, kind of same. Okay, so yes, all right. So the overall impact will remain the same, and that instance will not really get a focus. All right. All right. So we will also think of better possible answer. Okay. A question from Kamal is, I still feel that maybe giving lesser weights in the Gini score or something like that would be better. Okay. We'll just keep this in mind, and okay, we'll try to attempt it again at a later point of time. Okay, good. Very great set of questions. So, all right. These are questions that help us understand something. Okay. And all right. All right. So this is where we were. Okay. Now, to make the predictions, AdaBoost simply computes the predictions of all the predictors and weighs them using the predictor's weight alpha. And so while making the predictions, all it does is it computes the predictions of all the predictors, whatever we have trained so far. It feeds the same input data to all of them, and then weighs them using the predictor weights alpha. That means it basically finds the one which has got the maximum alpha, meaning minimum error rate. And the predictor class is the one that receives the majority of weighted votes. Okay. All right. So this is how the this is how the predictions happen. So first of all, it computes the predictions of all the predictors, correct? Then weighs them using the predictors weight AI, basically the one that receives the majority weights votes with respect to these weights. Okay, so so basically this is what it does. It's basically compute finds the one which is having the maximum predictor weights and uses the predictions. All right. So that's the way to do the predictions using AdaBoost. All right. A question from Kamal. Each predictor's weight is calculated only once. Yes. Yeah. So it basically it's only a single sequence. It doesn't go in the iteration. Okay. So in this diagram, these four algorithms will be in a sequence, and we don't again start from the beginning. A question from Mentao: why has the predictor such a weight alpha j? How can we use this criteria to calculate alpha j? Okay, so let's say we have four algorithms in the sequence. What we're going to do is they all have been trained on the input instances, right? They all have been trained on the input instances. Now, what we're going to do is we're going to feed this the input, okay, by okay, we are going to feed the input instance to all the predictors and see what are they predicting, then compute their predictors weight, all of the alpha j, as in j equals to 1 to all the algorithms, and then we pick the one which is getting the majority votes. Okay. All right. So this formula is used to compute the predictions based on the argmax. Argmax is nothing but find the one find the one which is giving the best alpha. Okay. So for each k, as in for each k, k here is, what is k? Um, I think k here stands for the algorithms, like all the predictors. K, no, actually for 1 to and find this. Okay. K is the K is the prediction, the actual prediction. Okay. The case is what it says is the predicted value is equal to the K. For the instances where predicted value is equal to the actual value and so on, predicted value is K, and we find that one having the maximum. Okay. Okay, so yes, I see the formula looks a little confusing, but the simple answer is that all it does is finds the finds the finds the predictor which has the majority weight votes. Okay, and these voting, the majority voting is done based on the predicted weights. Okay, all right, all right. Now, question is what is the significance of the predicted class? The significance of predicted class is the predicted class is the end result, right? We want to classify it as 5, 3, or something, is the one which gets the majority weighted votes. Okay, so Okay. Okay, a question from, okay, slide number 90. Yes, that's right, Binta. I mean, the formula is in item 3. Okay, this one. So his question was with respect to this one. Why has the predictor such a weight alpha this? Okay. So the alpha is a function of so what does alpha represent? So R represents the error rate. The smaller the R, the better is the predictor's. The smaller is the R, the better would be the predictor's weight. Correct? That's what this formula says. Okay. So all we do is in the end, we compute the predictor's weight, all of the predictor's weight, and then observe which one is having the best results. Okay, meaning the predictor whose alpha is the lowest is performing the best, and therefore we take the one that is giving us the best alpha. Okay, the the predictions of the one that is having the best alpha. That's right. Okay, a question from Inta is why can we use this formula to calculate alpha j, right? So yeah, okay, could you help me understand the question a bit more? I'm okay with taking a bit of time. Okay, how to infer it? So you mean that why does this alpha is inversely proportional to Rj? Is that your question? Right? So all right. Now let me just show you. I'll just try to put it in Notepad. So we say alpha. We'll say A equals A is alpha here. Okay. We're saying eta. Instead of eta, I'm just saying n, and we're saying log of 1 minus r by r. Okay, this is what it is, right? So if you look at this value, okay, let me increase. So we say n into, and then let's just ignore this part for now. This part, if you see, okay, it's not, I would say that it's not derived formula. It is more like an approximation. It's like a hunch that if we put it this way, then this would look, this would give us better answer. Okay. So all it is trying to do is this. Okay. So here we could have many, there could be many such formulas, and there are a couple of ideas here. One is that because what we are doing here is, one, if the error rate is low, this number is going to be bigger, and hence this number will also be bigger, and hence this number will also be bigger, and hence the whole value will be bigger. If this number is smaller, right, this number is really high, correct? So this number is going to be a it will be very small, and further this will be further smaller, and so on. Okay, so 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 as long as the R is zero point 0.5, zero point 0.5 is like random guessing. So zero point 0.5 means the, the R, let's say, what will be the R in case of random guessing in two classes? The R will be say zero point 0.5, correct? Because half of the instances will be right, and it'll be 1 by 2. right? So point in the case of point 0.5, this is going to be 2, and the a is going to be 0. So I think that's one of the reasons why we are subtracting 1 from this. Okay. Okay, but exact derivation, maybe we'll have to think about why these kind of cases that might have occurred, the one that I have just talked about, and therefore this formula was derived. So R represent the ratio of correct to wrong to correct, and that is obvious. But why did we come up with this formula is still not that obvious. Okay, and then whatever is the answer here, we put it exponent, and that is also clear. But this particular one isn't clear. Okay. All right. So that was our understanding of the AdaBoost. All right. So good. So that was how does AdaBoost performs. Even though we don't know what is going in the algorithm, still we'll be able to use it. But it is important to know that the, these algorithms are not such a big rocket science. All we had done is multiply it with certain number. Okay, probably here at this point, even if we just divided it with r or multiplied it with r, is still or divided with r, still the alpha could have been good enough. Okay, so we could also come up with these common mechanisms. Okay, so we do when we do the when we solve our machine learning problems, we would be able to ourselves come up with such ideas. All right. Okay, a question from Kamal. Let us say we use AdaBoost and try to predict a new image in MNIST. Okay, the first and second algorithm got predicted 5, while third predicted 4, and so on. Can you explain the formula in 93? Okay, so let me show you this. Okay, so basically here it's essentially a standard voting. The voting instead of based on the overall predictions, it basically computes the error rate. So all it will do is it will basically do the prediction every point, compute the R. Okay, let me try to say. Okay, so I'm just wondering, will it? The only question I have is in my mind that, okay, will it multiply by W's here, the 1 by M, before giving it to all the algorithms? Okay, that's a question I have. So it should ideally multiply all of them with 1 by M, because all the algorithms have never seen the values without 1 by M. But anyway, because it's standardized, so it should be okay. Okay, because it's normalized. So what it did was, let me just again explain what does it mean prediction. Let's say we have the first algo, second instance of the algo, third instance of the algo, and we pass the input to all of them. Okay, we got the output. We then computed the error rate at this point. Okay, error rate at this point. So they all got some error rate. Okay, then we computed the alpha based on the error rate. We computed this, and we picked the one having the best alpha. Okay, and the predictions of this one are going to be considered. So we first trained them, this line here. Let's say I draw this as training. This is how we did the training on this side. So here there were weight updates. This is where we did the weight updates, and we did that. Okay. No, so I think um, so yep. I think the sigma here. Okay, I'll say it this way. So what it is doing is, let me just show you. Okay, let me be very clear. So here, the answer, right? Here, answer is going to be what? What is the answer going to be? Answer is going to be the numbers, right? These coefficients, right? These coefficients. These are the answers going to be, right? And we basically it is going to be the decimal value. Okay, argmax generally means find the one which has got the max value. Okay, find the one which has got the max value. I think the sigma here, not really, it's not really a summation. Okay, all right. All right. So what we are doing again, let me just go over it. So we compute the predictions of all the predictors, that's right. Then weight them using the predictor weights, basically find the error rates, compute the alpha. Okay. The predicted class is the one that got the majority of weighted votes. Okay. So, okay, the error rate are computed based on that. That is alpha. Now, alpha we are doing here is, just give me a second. The alpha is not that. Okay, weigh them using predictor weights. Okay, weigh them using predictor weights. Okay, 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 okay. So here the term that's a little unclear is that on how are we computing alpha j and how are we weighing them? Okay. So, all right, we'll continue from here after the break and then we'll move on to the gradient boost and continue with PCA. Okay. All right. Great. All right. So let's take a break for 10 minutes. All right, so should we start? All right, so this is where we were. Okay, let me just take an example of, okay, so I'm not super clear about this part. So as per my understanding is that whatever alphas we have already computed for each of the predictors, right? Every predictor has some sort of error rate, right? So what we do is we let it compute the probabilities. Okay, we let it compute the probabilities. Then we multiply the probabilities of each algorithm with their alphas. Okay, the weighted ones. And then the class that gets the maximum vote out of that is the one which gets the correct answer. Okay, so let me just try to see in case of the 505 case. Okay, so in the 505 case, let's say we have new image we are passing to let's say there are instances. Okay, so we pass the same image to all of these. Okay, the first one is, let's say, having so the alpha values of, let's say, here it's zero point 0.4, it's zero point 0.5, and it's zero point 0.8. Okay, so the alpha is generally the confidence level of individual algorithm. Okay, so now let's say the prediction, these are the alpha values. I'll just put it in the box because that's the behavior of individual algorithm. Now, when we are doing the prediction is for this new image. This is a let's say for testing the let's say some new image, and we are doing the prediction, and the prediction is saying that give us what? It gives us a probability of yes and no. Okay, so the probability of yes and no is basically how much? This one is giving, let's say, it's saying the chance of it being 5 is zero point 0.4. Okay, all right, 0.4, 0.6. Okay, here we are saying whether it's 5 or not 5. First one means it's a 5. Second one is not 5. Okay, similarly, we have here, we have, say, it says 0.3 and it says 0.7. In case of this, we have, say, okay, and zero point 0.5. Okay, all right. So what we are going to do is we are going to multiply the confidence level of each one with this predicted value. So it's going to be the in this case, let's just take the first case, for example, here. So 4 into 4 is 0.16, 0.16, and this is 0.15, this is zero point 0.4. Okay, so in this case, let's say it's zero point 0.4 in both the cases. Now here it says the okay, so the majority of votes, who has received the majority of votes? Here in this, the other one, okay, is the class. So this is 0.24. This is 0.35. And this is 0.4. Okay, so probably in this case, the majority votes is okay. Predictor is the one with received the majority of weighted votes. Okay, so here I think the way we do is we basically sum it up and then see what is the overall. It's basically softmax. soft voting, and here this plus this plus this, which one is more? So this one we can ignore. So this plus this. So here it's definitely not 5. Okay. So this is what my understanding of the algorithm is. All right. So we sum up all the probabilities and then see which one is the max. The important part is that we basically let the algorithm do the prediction. Okay. And once it has done the prediction, then we multiply the predictions by their alpha values. Okay, alpha values was what? It was basically how much each algorithm is, right? And that's how we get the outcome. All right, did it make sense to you? All right, so this is what my understanding is of this algorithm. Okay, we basically, I think this is soft voting. Okay, and correct, correct. Then a clear statement would have been sum of all the weighted predictions. Okay, sum of all the weighted prediction. So I think here when we say soft voting, I think in soft voting we call this as majority weighted votes. Correct. That's why this sentence. Never mind. So this is probably the way it is. So we'll just go into more details at a later point of time, as in um, okay, let me just put a comment here saying clarifying. Okay. Actually, the argmax, okay, argmax is, how should I say? The argmax generally represents the class that has got the maximum vote. Okay, find the argument which has the max value. That's what argmax means. And from the argmax, I'm getting the feeling that it is going to be hard voting. So at this point of time, the question is, this is what happens. This is what happens, right? So we multiply the predictions of each algorithm by alpha values. And then whether we are just checking who has got the maximum value, say this one has got the maximum value, okay? Are we just checking that part, or are we are we doing the soft voting? So at this point of time, the one thing that is not clear to me, whether it's hard voting or soft voting. From the wordings of this one, it sounds like, okay, so just look into it into more details. Okay, so that's the only clarification that's required. Never mind. So basically, this is how the AdaBoost does the prediction. The only thing that needs to be clarified is whether whether it's the soft voting or hard voting. That's what we need to do. Okay. Yes. The other problem that I foresee in this formula is there is no multiplication of the alpha value from the actual prediction, and I think that we'll have to correct it. Okay. So I'll just put it here, and why the predicted value isn't multiplied. Okay, because it says weighted clearly, and yeah, so that probably this needs to be revisited. Okay, so in scikit-learn actually uses a particular multi-class version of AdaBoost. It's called SAMME 16, stage-wise additive modeling using multi-class exponential loss function. Okay. All right. Moreover, if the predictors can estimate class probabilities, right? So it's actually impossible to, it's like a tongue twister. So, okay. So basically, okay, so can somebody say it 10 times? No. Okay. So, so when basically the same one that we've used just now, the one that we talked about, the same one is created as multi-class, and that's what is called as SAMME16. Okay, when there are just two classes, then this algorithm is equivalent of AdaBoost. Okay, so the one that we use in scikit-learn is this same 16. Okay, moreover, if the predictors can estimate class probabilities, okay, okay, if the predictors can estimate class probability, that is, they have predict prob method, scikit-learn can use a variant of SAME called SAMME.R. R stands for real, okay, which relies on class probabilities than predictions and generally performs better. Okay. So, okay, so it looks like that. Yeah, actually, in most of the cases in the whole algorithm of AdaBoost, we did not rely on probabilities. We only relied upon the right prediction. Okay. So, yeah, and probably, hmm, hmm. I think I got this one now. I can explain it a bit later, maybe. Okay, but let's carry on. So we basically could visit it at later point of time. I'll just put it more visualization to it, put more diagrams to it. So probably that will help understanding it. Okay, so the following code trains an AdaBoost classifier based on 200 decision stamps. Also, please note that AdaBoost, the AdaBoost is specifically great in case of weak learners. If you figure out that the problem you are trying to solve, okay, for that particular problem or the particular case, the algorithm that you're using is really a weak learner, okay, is really a weak learner, then you can use the AdaBoost kind of algorithm to improve its performance. Okay, so AdaBoost is great for really weak learners. So here is the case where the AdaBoost classifier is basically training decision tree classifier with max depth 1. The stump means max depth 1. Okay, so the basically it has kind of only one level of a tree. So basically it's going to be really weak learner. And the number of estimators we are saying 200, algorithm is this one, and learning rate is 0.5. All right. So here we are doing the fitting. So, all right. So here, in other words, a tree that's what is the AdaBoost, the decision stumps. Decision stumps are basically single decision node plus 2 leaf nodes. Okay. So this is how we have done the training. All right. Next is, let me just pick the example here. Where are we? Is it there somewhere? Okay, so here we are saying, let me zoom it out. Okay, here we're saying AdaBoost classifier, decision tree is this, max depth is this, number of estimators, and here we go. Okay, do I need to run everything above? Okay, so ADACLF is an instance of this class. Okay, Vinta. So ADACLF is an instance when we are creating an object of this classifier. This is the one. Okay, and then we are calling the fit on it. How to choose the value to the parameter for this? Which parameters are we talking about? Okay, so here we have just fitted it, and rest of it has done internally. And so if we are asking it, we are using our function called plot the decision boundary. This is how it looks. So even a decision stamp of say one one label, it's actually doing really good here. You can see that it is actually doing really good. Okay, and yes. Okay, so here we have explicitly used max depth just to demonstrate that AdaBoost can really boost even the weak learner. The smaller the depth is of decision tree, the more it is underfitting. And that's why most of these algorithms that we use with AdaBoost are generally the ones that are underfitting. They're performing bad on the test data as well as training data. Okay, so and we have forced it here just to demonstrate to max depth, and we are showing that number of estimators are 200. The algorithm is this one. Learning rate 0. 0.5 is generally good learning rate in these cases, and again learning rate you can start with 0.5 and then experiment which one is performing good. Okay, so so that's how it is, and here we go. Okay, so I hope this is clear to all of us. Okay, so here we are plotting the decision boundary, and here we go. So all right, then okay, and you can see that when we increase the learning rate, the overall impact is higher. Okay, okay. So the various functions that you see in case of the 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 these are the internal functions provided. So that's what we have demonstrated. All right. So great, great. So we were able to fit and train. And so if your AdaBoost ensemble is overfitting the dataset, you can try reducing the number of estimators, or more strongly regularize the base estimator. Okay. So generally AdaBoost is used with the algorithms which are underfitting, meaning which are really weak learners and have higher bias. Okay. So just like, okay, great. So now should we start with gradient boosting? Okay. A question from Gopi is, for AdaBoost, what is the perfect predictor? And okay, the stopping criteria. Okay. The stopping criteria is this. If you can see if the moment, generally the stopping criteria as such, stopping criteria essentially means what should be the value of this? What should be the value of number of estimators, correct? That's the stopping criteria we're talking about. So we put one learner, then another, then another. Here we are putting 200 estimators or 200 predictors in the sequence. Okay. So it is going to do 200 times. Evaluate only once, but 200, it is going to create 200 decision tree classifiers under the hood and put them in the sequence. Okay, put them in the sequence. So here we could take a look at the ADA classifier. So we have base estimators, decision functions estimators. Okay, so it can show that these are the various estimators chained, the 200 estimators in the queue, in the chain. A question is, how would we know the 200 is an overkill? Again, we'll basically measure if it is underfitting or overfitting by doing the standard hyperparameter tuning. That is the only way to basically reach to a level. The moment it starts overfitting, so if the number of estimators are really low, it will underfit the data. If really the number of estimators are really high, it will start doing the overfitting of the data. So we'll have to find that number where we are going to be on balance between the bias and the variance. Okay, so we'll have to find that number by doing the hyperparameter tuning. Okay, so a question from Gopi. So when it is stop, okay, a question from Gopi is, so when will it stop computing and readjusting the weights? Is it after 200 iterations, or when will it stop early? Okay, so basically it is going to line up 200 decision tree classifiers, and while we are feeding, it'll keep on going, and probably there could be a scenario, right, where it has error rate is 0, correct? Probably that point onwards, when the error rate is 0, all the algorithms would not play much of a role, right? When the error rate is 0. Yes. So I think that could be one of the parameters here. So yes. So maybe that's the way it can stop early, because the alpha will automatically go to I think 0 itself, or infinite. I don't know what will happen in case R is 0. So if R is 0 at any point of time, that means we have overfit the data, and yeah, that way. Okay, so all right, we'll take a look at exactly the stopping criteria. But as per my understanding clearly so far, is that we generally consider number of estimators here as hyperparameters, because if you decrease it, it goes towards underfitting. If you increase it, it goes towards overfitting. Therefore, we need to find a fine balance of it. And okay, okay, we will look into it further. So we'll just put it somewhere in our notes. Okay, stopping criteria for AdaBoost. Good, great set of questions. And all right, all right. Should we start? Now, the next important concept is gradient boosting. Okay, just like AdaBoost, gradient boosting works by sequentially adding predictors to ensemble. Okay, each one correcting its predecessor, and but instead of tweaking the instance weights at every instance like AdaBoost does, this method tries to fit the new predictor to the residual error. Okay, so instead of the way what we did in case of AdaBoost, that the instance weights we kept on tweaking, and then we kept on feeding it to the algorithm, right? So In this case, what we do is we subtract the we basically compute the residual error. Okay, we basically compute the residual error, and then we train the predictor on that. Okay, let's try to understand how gradient boosting works by using decision tree as the base predictor. Okay, all right. So let us try to understand the how gradient boosting works by decision tree. So here are some of the steps that we will do. First, we will fit decision tree regressor to the training set. Okay. So gradient boosting, we are going to go with decision tree regressor this time. Next, train we'll train second decision tree regressor on the residual error made by the first predictor. Okay. So all right. So, and then again, we will train the third regressor on the residual error by the second one. And then we will have an ensemble containing three trees. It can make predictions on new instances simply by adding up the predictions of all the trees. Okay. Say, for example, here, let's generate this random data. It's a quadratic noisy data. Okay. And we are fitting it here. Okay, so we are saying np random, we are setting the seed, we're generating x is nothing but some random value. Okay, and we are subtracting zero 0.5 from it so that it becomes from minus 0.5 to 0.5. Next is that we are defining y. What does y do? Y basically is 3x square plus zero 0.5 into some random number. Okay, so it's a quadratic data with some random coefficient to it. Okay, so next we will fit the decision tree regressor to the training data. So here we're saying the depth is 2. It's not really a stump, but it's a with the depth of 2. Then at this point we are fitting the data, we are fitting x and y to it. Okay, now next thing we do is we compute the delta by. Okay, we do the prediction on the same data and then do the computation of delta y. Okay, y minus the prediction. So this is our new value. Okay, now this time what we are doing is we are this time after computing. So at this point what we are doing is we are again calling the same method, and we are fitting the x and y to. Okay, instead of xy, see here we basically trained it on x and y. This time we are computing, we are training the second algorithm on x and y too. Okay, now in the second stage we are subtracting, we again doing the prediction from this, we are doing the prediction from this, and then we're fitting this uh, the new algorithm on the residual error done by this prediction of the first one. Okay, so this way we got, finally we got three algorithms, the three trained algorithms, each one on the predictions on the residual errors. So all we need to do is at later point of time, in order to get accurate predictions, take the each decision tree, train them, and then we do the prediction on each of the decision tree and sum up all the values. Okay, sum up all the values, and that way we'll get good results. So it's actually pretty straightforward. So here we are saying that tree, so here we are saying for tree in this, and we are summing up all the values. Okay, if this is confusing to you, I'll just show you. Okay, and here we go. So we have gradient boosting. So here we're generating data x and y. Next, we're training our first regressor. Okay, we are training our first regressor. So this is basically, this is what we are doing. Then we are predicting and computing the error. And then we are training the second regressor
on this new y2. Okay. Now then we are creating a third one, third regressor, which is being trained on the errors of the first one, previous one. So we're chaining them together, and that's how we got three algorithms. And we can now, let's say for value of zero point 0.8, we should ideally expect what value we should expect for zero point 0.8. 3 into zero point 0.8 is square. Okay, 3 into uh, yeah, 3 into zero point 0.8 square. Okay, which is 3 into zero point 0.64, and 3 into 0.64 is 1.8 something. So, okay, so this is the y predicted value. Oh, did I make mistake in the calculation? So we are saying in case of this, okay, so we are saying 3 into zero point 0.8 square. Okay, 1.92. Okay, so we have x new containing 0.8, and we are predicting the value here. X new is some new number that we are going to use for prediction. Okay, I'm just wondering why the accuracy is so low. Okay, never mind. So let's just move on. Now here we are saying that for this is equal to a for loop, right? For tree in this, and then we are basically creating an array called tree here, and then sorry, we're creating this value. Okay, it's going to be basically tree reg1 dot predict, tree reg2 dot predict, tree reg3 dot predict, and so on, and we are computing the sum of that. Okay, so this is the y predicted value. Y predicted value is this much. Or should I break it down further? We'll say array, okay, y predict array equals, okay, so it essentially is, okay, and then we say y predict array is this. Okay, so the value of y predict array is this, and individual predictions are these. Okay, so in the first one's prediction was this much, second one's prediction is this much, third one's prediction is this much. Okay, and we are just summing it up. Okay, we just chose 5 for whatever reason, and okay, because these values are somewhere between okay, let's just see the capital X, how does it look? So most of the capital X is actually between minus zero point 0.5 to 0.5. That's the reason I think it's giving the wrong answer. So if we have, let's say, zero point 0.4, right? If we had like 0.4, then answer is going to be better. Right. So you can see that when we did predictions for 0.4, the answers were close to the actual one, while, okay, while if we did the predictions for 0.8, the answers were far, far away. Okay. Okay. So it essentially means that this is also kind of an overfitting it. Okay, now, all right. So this is these three blocks would help you in understanding. Okay, so what we did was, let's say the first block, this is first algorithm, this is second, this is third. Okay, so we had here some training instance, right? Along with target values. This is input data. This is the target values. Okay, so here there were some input data was there, and there were values of x and y, and then we did the first we did the training. We did here, we did the training, and okay, we did, let's say here the training is happening here. Okay, and then what we did was we did the prediction here. We did the prediction. Okay, we did predict. Okay, we did the prediction. Now prediction basically generated the new set of y here. We subtracted these two, okay, and prepared the new data, which looks like, so I'll just, this is the new data. This portion specifically is, so this one generate, after we predict, there will be new set of y, right? This is y1, this was y, okay? Now what we do is we subtract these two, this and this, and we put the value in this one, while this remains as such, okay? And that becomes, that's what we feed to this next algorithm for training, okay? All right. So basically, whatever y values we had earlier, we take these, subtract from the new prediction, we subtract the new predictions from it, and then the delta value that is generated becomes the new y. The actual instances remain the same. The actual instance values, x, this is x, right? That remains same. Okay, and the same thing will be done again. Now, when we are doing the new prediction like y2 here, so we'll subtract these two, this and this, and generate a new value. Okay, so that's what we are doing. So we are computing y2 equals y minus predictions, and then we computing y3 by doing y2 this minus new predictions. Okay. All right. Is it clear to everybody? So here we try to plot the predictions. So it's the same algorithm, yeah, right? And it's trying to fit the data there here. And yeah. Okay, so let's walk over these diagrams once. The ensemble has just one tree, so the predictions are exactly the same as the first tree's prediction. All right, now in the next step, the new tree is trained on the residual errors of the first tree on the left. So on the right, you can see that ensemble's predictions are equal to the sum of the predictions of the first two trees. Okay. Then we go for the third step. Then we do the predictions. This is how it looks like. So finally, as we are adding more and more trees, the predictions are improving. You can see that it is going towards more overfitting from underfitting. Here it was underfitting. Here it is more towards variance from the bias. Okay. So after third step, another tree is trained on the residual errors from the second tree. The ensemble's prediction gradually got better as trees are added to the ensemble. And okay, so this is how it happens. So in practice, you might have like 50 trees in the sequence, and we could do the gradient boosting. So a simpler way to train gradient boosting ensembles is to use scikit-learn's gradient boosting regressor. And so gradient boosting is generally used for doing the regression, while the AdaBoost is generally done for classification. Also, the AdaBoost is also often used in case of weak learners and the one which don't have the probability method, okay, in which we don't have the probability computation. That's another bit of information. So because a lot of time when you can't do the probability, then you also use the AdaBoost. Okay, because the probability is only required in the last stage, right, for the prediction. Okay, there you can anyway go with hard voting instead of soft voting. All right. Okay, that's right, Noor. Okay, so we will do a similar walkthrough, maybe through the AdaBoost. AdaBoost is a bit more complex than gradient boosting. Gradient boosting is actually a little bit more simpler. That's why. A question from Noor is, how will this work for classification? Okay, how will this work for classification? Yeah, so I doubt if, let me just think over it. So gradient boosting is generally used for classification. And is there a gradient boosting classifier? Do we have that? They do have, yeah, they do have classifier, definitely. Okay, so let's just go over, do we have that as we go further? Okay, now going back. All right, so in the gradient, what will it do in this case? How will it compute the errors? Probably the errors it would compute based on, okay. Question is that if we are using the classifier, if we are using the classifier instead of regression, how will it work? Probably what, maybe the probabilities is what we'll subtract. Probabilities of various classes is what we'll subtract instead of this, and probably that's how it'll work. Okay, so instead of the actual value here, we'll be subtracting the probabilities, and that's how probability will work. Okay, thank you, Gopi. So it seems to use the log probabilities in case of the classifier. Okay, good, good. All right. So gradient boosting is generally used for regression. Okay, but you can definitely use it for classification. All right, good. Moving ahead, so a simpler way to train using this class, and just like random forest regressor, its hyperparameters are same as decision trees, and we can We can specify max depth, that min samples, which are the hyperparameters of the decision trees, and we can also control the number of trees that we would want in the sequence by using n estimators. And so here in our case, this is what we actually did. This is what we actually did. We used max depth 2 and number of estimators 3 and learning rate as 1. We'll talk about learning rate. Okay, so what we have here is the one that we did earlier is basically the one that we have done earlier. We basically used the learning rate as 1. Okay, so here, if we just increase the estimators to 200, then it is going to be a bit slow. Okay, and let's just plot it. Okay, all right. We'll just go over from here onwards. Okay, so this is okay. This is okay. All right. I think I missed some of the. Okay, so we'll talk about this very soon as we go ahead. All right. So basically, this is what gradient boosting is about. Now, these are the various parameters that we can regularize. So learning rate hyperparameter scales the contribution of each tree. It scales the contribution of each tree. If you set its value to 0.1, you will need more trees in the ensemble to fit the training set, but the prediction will usually generalize better. Okay. Probably at this point, we would be multiplying this learning rate with the delta of y2 and y1, and then be using the contributions accordingly. So this one resembles, this ensemble are trained with low training rate, hence they do not have enough trees to fit the training set. And so here we have learning rate as 1 and number of estimators as 3. Okay, we have learning rate as 1 and number of estimators 3. This is the one that we were doing so far. Okay, when we decrease the learning rate, meaning we decrease the contribution of each learner in this. Okay, each learner in this, probably we would be, okay, we would be multiplying the delta by some value. Okay, so in that case, it will kind of overfit and do a better learning than this. Okay. All right, how to find optimal number of trees? That's a very important question. So in order to find the optimal number of trees, you can use a technique called early stopping. A simple way to implement this is to use staged underscore predict method. So it returns an iterator over the predictions made by the ensemble, okay, at each stage of training, first with one tree, then two trees, and so on. Okay. So let's just take a look. Did we use it here? Okay, I think I have an older one. Staged. Okay. All right, let me just take a look at. Okay, I think the I'll just get the notebook committed if it is around. Let me see if it is happening. Git checkout. Okay, so all right, I think that piece is not there. All right, so okay, never mind. So the sole idea is to use the early stopping, and we will get it fixed. Okay, so the simple way is to use the early stopping, and we should have staged, right? Okay, I think the code isn't there yet, so probably we haven't committed that piece of code. Okay. All right. So now, okay, we'll look into that particular piece probably later, and basically there is, yeah, we'll get this piece done. Okay, so the following code trains gradient boosting ensemble with 120 trees and then measures the validation error at each stage of training to find the optimal number of trees, and finally trains another GBRT ensemble using the optimal number of trees. Okay, so basically here what we have tried to do is we have tried to plot the data with number of estimators. Okay, so as the number of estimators are growing, you can see that it has grown to that. And here we are saying, okay, gbrt.learning rate is what we are putting there. Okay, we have created two gradient boosting regressors, one with the number of estimators is 3, while learning rate is 0.1, other with number of estimators is 200, but learning rate as 0.1. And below, we are trying to plot it. So let's just take a look at this. So basically here we are trying to show that if the number of estimators grow higher in number, it is going to kind of do an overfitting. Here it is going to do underfitting because the number of estimators are low. And as the learning rate is really low, therefore the impact of each individual estimator is lower. Okay, so that's what is about the. So in general, what we do is we fine tune these parameters, the estimators, and the learning rate to fit to our requirements. And also the most of the boosting techniques, whether it is AdaBoost or gradient boost, is used with weak learners, the learners with low uh, low variance and higher bias. As in, the learners with higher bias is what we train it on. We basically use the boosting techniques, AdaBoost and gradient boosting, with the ones that are bad learners. Okay, so that's pretty much about this. Okay, all right. So there is a way to stopping early. A simple way to implement this is using staged underscore predict method. It returns an iterator over the predictions made by the ensemble at each stage. Okay, and we can basically stop whenever we want. Okay, so that's the one. All right, so that's pretty much with respect to ensemble and random forest. So should we move on to the next topic? A question from Gopi. So instead of specifying number of estimators manually, we have optimized and used the n best estimators. Okay, yes. So in this case, we have specified ourselves. Okay, I'm just trying to see if we could. Okay, okay, let me just try to see if I could. Let's go predict. Okay, so let me just go over this. Okay, so I'm just trying to see this. Okay, so probably this kind of Okay, so this is what we were talking about in the case. Yeah. All right. So what we were doing is this is what the code wanted. This is what we wanted to discuss here. So here, instead of simply calling predict, what we could do is we could use a method called staged underscore predict on some value, say x underscore test or something, and then it'll basically keep on giving us keep on calling this method as in this particular piece of code as in when there is a new predictions. Okay, so basically here it's giving us predictions as it's going ahead, and we can stop whenever we want. Okay, so that's the one that he's talking about. So a simple way is to implement. So we can basically you decide upon a particular error rate, and in order to find the optimal number of trees, we can stop whenever we want. Okay, so one way would be that whatever is the loss that we have here, if this loss is greater than if this loss is lesser than point, let's say point zero zero one. Okay, we can just stop here. Okay, so okay, did I do something wrong? Let me just print it again. Okay. Okay, let me just see the value of this. So if I'm saying here, we could say if this value goes below this, okay, I'm saying if x is below this, then we say break. Am I doing something wrong here? No? Oh, we are not printing it actually. Okay, so it's correct only. So this is called early stopping. So we can stop when our loss is something which is tolerable. Thank you, Noor. Thank you, Noor and Gopi. All right, good. So this is what is, okay. So yeah, so we were able to quickly implement this piece of code, and I think this was useful. So this, I think there are many algorithms that provide you stage predict. Probably the other methods are also there. Other say AdaBoost would also be having similar thing. Okay, so this is a way. I hope this is clear to us. So instead of yeah, enumerate basically gives us the iterator, and over the iterators we could actually go as in start moving. So enumerate gives us the handle to enumerate over it. I'm just trying to see if we just remove enumerate, what will happen. Okay, it expects the it basically wants it basically is giving us iterator, and then we can iterate on it by using the if it has next or not. Okay, so enumerate converts that it converts that iterator on. Okay, let me just say. Okay, so if you want to use the for loop over the iterator, we can put a method called enumerate. Enumerate converts an iterator into individual values, and it starts giving us. So at each stage, the iterator is giving us a tuple of values. The one is the I value, and the other is predicted value. I is probably the stage. Let me just say it's probably the ith stage. Okay, yeah, you can see 0, 1, 2, 3. So it starts there. Okay, so basically either this way you will know here that this precision has been achieved at this at ith tree. Okay, so here you can see that 29 is the number of trees that we should use, because this number starts from 0. So for achieving this accuracy, for achieving this kind of accuracy, we need 29 stages. Okay, to achieve this kind of accuracy, we need 29 stages. All right, did it make sense to you? We need 29 estimators. That's right. All right, good, good. So a question is, can you plug 29 into n estimators and see if we get the same results? Yes, you should try that. Okay, so here, okay, gradient boosting, then this is the same one, right? Here, and we could say number of estimators. Okay, number of estimators is how much? Say 29, and we are fitting it, and here we should see the loss. Okay, so when we are predicting it, okay, so I think this should be same. So yeah, it's kind of same. All right. Correct. All right. So yes, so basically our assumption with respect to the stage predict is good. So should I commit it? All right, I pushed the changes. All right, good, good. So basically what we learned was the stage underscore predict method basically is a cool method, and it basically runs the things in, it gives you the control back to you so that you can stop whenever you want to stop. Okay, so and we can just break, and that's the point where it won't go beyond. Okay, and all right, this is basically an example of early stopping. Good. Now, so, all right. Now the validation error varies as shown below. As we can see, the best value for n estimators is near 55. Okay. So as number of tree grows, the validation error keeps on growing down. And after a point of time, the no matter how many trees you increase, the validation error will not go down. Okay, so this is an important part. So So basically, after a point of time, this will anyway stop, this won't go below a certain value. So we have to keep that in mind. This validation error could be because of the wrong data. This could be because of randomness in data, as well as it could be because of the algorithm not being able to predict it. But most likely, this error, this consistent error, is going to be most likely the randomization in the data. Okay, the best model's prediction as shown below, it is constructed with 55 trees. So yeah, so this is an example of a good model. Now, it is also possible to implement early stopping by actually stopping training early instead of training a large number of trees first. And then instead of training a large number of trees first, and then looking back to find the optimal parameter. Okay, so okay, and you can do so by setting warm start as true, which makes scikit-learn keep existing trees when fit method is called. Also allows incremental training. Okay, so in almost every algorithm, there is a there is a parameter called warm start equals to true. Okay, so what does warm start equals to true does is it basically retains the same the previous parameter of an algorithm. So if you're calling the fit method again, it will start from the previous values. It won't start from the beginning. So if you say warm start equals false, then it will override the old values and forget them. So the one way is that we basically start with few trees. Okay, we basically, instead of training on large number, it is also possible to implement by actually stopping early, meaning that you start with set entries, then observe how it is going, uh, then then train on 10 more trees, and so on. So this way you'll basically continue from where you left off. Okay, so just we have to mark it warm start equals to true. Okay, so that's also one way of going up, because if we start going to 500 trees, it might not finish ever. Okay, so this is also another technique. Correct, that's right, Gopi. So optimization is a function of experimenting with hyperparameters, and the other thing that we have discussed is using the early stopping. And one way is by using the stage predict, as in we put the constraint and early stop, or we manually stop early and then we move further. Only we first say 10 and then see how it goes. Then instead of retraining on those 10 which we have already done, we basically train again. Okay, so that for loop could also be done in the same way to achieve the same thing. Okay. Question from Noor is, what my understanding of warm start true is that you can run the algo instance wise so that it is applicable at estimator level or instance level. So actually, I'll tell you what it means. So let's say we have this here. Okay, I'll tell you. So let's say we were having say 10 estimators. Okay, and we say okay, and we say warm start equals to true. Okay, warm start equals to, okay, is equals to true. So here what will happen is that it will basically keep this there, and okay, and instead of say 10 are the estimators, right? So we could just call this method twice and see what is the loss. Okay, so you can see that the loss here, I'll just print this loss in both the cases. Okay, All right, so let me just see. Okay, so basically the idea of maybe it's not working correctly here. Or maybe we might have to break it down to, okay. hmm Okay, so maybe this one is not honoring the warm start. Okay, all right. So the general idea is that if you call the fit method, it basically improves the existing one instead of calling it again. Okay, so if we, maybe we'll need to just change this 0.4, 0. Okay. hmm Here it doesn't seem to do the warm start equals to true. Does it have a method which does? Okay. Ideally, what happens is when we have used it multiple times earlier also, the warm start equals to true. In the case, what happens is when you call the method fit again, it will basically improve the existing tree. Okay. So it will improve the existing tree instead of the new one. Okay. Instead of creating a new instance. Okay, so I think this is an example of early stopping. The following code stops early when validation error does not improve. So here is the another strategy whereby we are saying gradient boost regressor. We are saying depth is this much and so on. And here we are saying warm start equals to true. Okay, and minimum error is say infinite. Okay, then we are saying error going up is 0. So we are saying number of estimators are between 1 to oh, say 1 to 120, and we are calling number of estimators here. Okay, we are setting this number of estimators here. Okay, so we basically are saying here fit and then predict and then showing the mean squared value. And okay, so if this is there, we could stop it or we could go up. So if we have reached a validation error which we are looking for, okay, then that is good enough. Otherwise, we could break early. Okay. All right, let me just format this code. Probably that'll be better. Okay. So if this is, we copy paste this code. Okay, so we are saying this is our regressor, then we're defining this value. This is good. Then we are, okay, after for loop, everything is in the loop. Okay, so we are saying number of estimators, fit, predict, and then this is where we are doing the early stopping. Okay. Okay. All right. right, so what does it say? It says x underscore validation is not defined. Okay, we might have to break our data such that we have two sets. Okay, so we don't have, okay, the training data. Let me just put y and y for now. Okay, so what does it say? Okay, so did we overwrite some values here? All right. Okay, so capital X is something which we need to figure out. I think we just need to break our data into some parts. For now, let me just try using this and see how it goes. Okay. Let me import scikit-learn. Did the mean squared error. Okay. So all I need is we need to say from sklearn dot matrices import this. Okay, so it did not break up early. It actually finished all of this. So we could say here, instead of minimum validation error, we could say things like that. Still, it did not work. And we could print here, print. Okay, so this is where, actually it is stopping early. It is just not showing. Okay. All right, so yeah. Yeah, so what's happening is that if the moment that it notices that the error is going down, or actually the previous logic was also good. Okay. Okay, so I'll explain again. So here, this is a very interesting part. So what's happening here is that it's noticing that if it is going up for 5 times consecutively, it'll break. Okay, it'll break. So otherwise, it will keep on improving. Okay, so this is what is happening. So here what's happening is it has finished all 120 rounds and the error did not go up. Maybe because we are using the same data set. All right. So should I explain again? So what's happening here is we defined a gradient boosting regressor. The max depth is 2 and warm start equals to also true. Then here we are defining a minimum validation error, which is infinite. Okay, so we are saying that the error going up is a 0, and this is the variable that we are using in order to track the in order to track for last how many times the error has been going up. So we're calling this this code did not enter the else block as such, right? So what's happening here is that the number of estimators is say 1 to 0. So once from starting from 1 to 120, and here it's saying that the it's setting the number of estimators and then calling the fit. Okay, so basically when we call it this way, it essentially uses the previously trained data when we say warm start true. So it basically uses that, and then we doing some prediction, but the only problem here is that we are using xtrain itself to do the predictions. Okay, so let me see if we could find the if we could use some other variable. What was the name of the variable that we used earlier? Okay, okay, we have xtest and ytest, right? I'll just use this xtest and ytest. Let me just try to use xtest and ytest here. In case of prediction, we are saying xtest and ytest, and then see. Okay, so here this time it is stopping. So now you get Noor, why it wasn't stopping? Because error wasn't going up, because we were basically testing on the same data as on which we were predicting. Okay, so what we are doing here is basically the we are observing if the error is going up 5 times consecutively, then we are stopping. Okay, so this is another way of early stopping. Okay, there were two ways we talked about. One was using the stage predict, as in we can stop actually, and second one was using the warm start. So warm start will remember the previous trainings, okay, and will basically add to that one. Will add to that one instead of starting from the beginning. All right. So this is how we do the early stopping. We talked about two example cases. One using the where did it go? Don't tell me. Okay. Yeah. Here one using the stage predict and other using this mechanism of warm start. All right. So this way we can do the early stopping. All right. Sure. Let me just commit this code. And I'll just call this last command. All right, so okay, all right, we'll continue from here in the next session. There are something also called stacking. We can stack one predictions on top of another and then do the blending from each predictors. We'll talk about this one and start PCA next session. Okay, so we have 2 more sessions left. So in one we'll discuss PCA as well as this, and other we will cover the couple of things that we have talked about. And okay, yes, time series is one. Okay, time series is one. Okay, the other one was XGBoost that we have talked about earlier, and there was knife. I have to review that part as well. Okay. NLP, yes, that I have noted down. There was one more question related to naive Bayes, right? Yeah, yeah. Okay. Just see, because there was a reason why there is a good reason why this curriculum was designed. Okay. So this curriculum generally covers most of it. NLP we are covering in deep learning, and time series we'll have to see how we are going to accommodate. Okay. So we'll have to review these few elements. Okay. All right. So that was, yeah. All right. So some of the goof ups for today that we had not updated the notebooks, but I think we'll be able to handle that. Okay. Great. Great to have all of you in the session. I will update the, I'll update the notebooks further and we'll stay. Okay. Okay. Yes, that is one thing. At least the prediction part we should be able to do. Let's just see that if we can do that. Okay, good. Great set of questions. I look forward to see you next week. Thank you, everyone. Thank you for wonderful set of questions. And yes, topic 3 tutorials is something which we need to do. Thank you, Binta. All right, wonderful set of questions. I look forward to see you in the next session. Bye-bye. Yes. Yes, there are so many models and it's overwhelming, but good news is that we have grid search as well as we have hyperparameter tuning, so we don't have to worry about much. Okay, thank you, Noor. Look forward to see you in the next session. Bye-bye. Have a good day.